So let's get started. What you're looking at here, this is a picture of the European gas network. And well, as you can see, it is quite complicated. It has these junctions, nodes. Well, it's very complicated. But there's good reason for that. Because in the Netherlands and many other European countries, we use natural gas to power our industry and to warm our houses. So to make sure that there's always an ample supply of gas available, we have these things called gas storages spread all over the network. So if you look around Europe, there are quite a few of these gas storages. And the way this works is that during the warmer summer months, the demand for gas is lower. So at that time, energy companies purchase natural gas on the market and they store it in one of these gas storages. And then when it gets colder and demand goes up, so prices go up, you can see that the gas storage is being emptied again. And by the difference in price, the energy companies using these gas storages can make a profit. And the country as a whole benefits because there's always enough gas available. But first of all, let me introduce myself. My name is Loek Duys. In the Netherlands, O and E is pronounced OE. So it's kind of like Luke Skywalker, I always say. That resonates with a lot of IT people. I am a CTO and cloud architect with a Dutch consultancy firm called Xspirit. And, well, if you want to get in touch, you know what to do. Over the past years, I've been working with a team for a company that operates one of these gas storages. And the cool thing about this company is that they offer this gas storage as a service to other energy companies. So the way this works is the operator, they paid for an empty gas field and they put this huge factory on top of it. And, well, there was no gas anymore in the gas field because, well, it had been used. And now they use it as a kind of a parking garage for natural gas. But it's so huge, this one company, it doesn't need all that space. So they decided to rent out the remainder space to other energy companies and, of course, send them an invoice for that. So customers, they will inject or withdraw gas from this storage. We've seen that in summer, generally, we inject into the gas storage, and in winter, generally, we take it out. But each customer can decide for themselves whether they want to put stuff in or get it out. The important thing to realize here is that the input must always match the output. So whatever is being consumed at the industry side or the houses side needs to be produced, put into the network at the other end. If you take too much gas out of the network, well, the flames will go out, of course. But if you put too much gas into the network, the flames may go higher than you think, and you'll get fires. So this is a very time-critical and mission-critical process. So the amount of gas flowing through this network, it is huge, and any deviation can cost, well, thousands or maybe millions of euros. Well, to give you a little bit of an idea about the size that we are talking about, this gas field is located somewhere in the Netherlands, about 2.5 kilometers below the surface of the Earth. It can contain 8.4 billion cubic meters of gas. And well, that is a number that doesn't resonate probably. So I put it in different words. About 6 million households can run on only this field for about a year. Or the whole country of the Netherlands for about 2 months. It produces, or no, it stores 48 terawatt hours of energy. And you can either inject or withdraw with about 400 to 500 gigawatt hours per day. So really huge numbers. Before we dive into details, let me ask you, does anyone here ever work with Azure on a daily basis maybe? That's good, because I have a lot of Azure stuff. And does anyone here already build a mission-critical system? Oh, just a couple of those two. No, really nice. Well, I hope you can learn something. Okay. What I mean with mission-critical system is that if there is ever an outage, you want the amount of data in such a system that can be lost, that you can tolerate to lose, close to 0. So you want 0 bytes of data lost. The time to recovery after such an outage, you want it to be close to 0 as well. So, well, whenever something goes wrong, the system should be up and running immediately after about 0 seconds. Well, that is, of course, a very tall order, because the closer you get to 0, the higher your cost will be. And it will even go exponentially the closer you get to 0 downtime and 0 data loss. You will need to introduce a lot of complexity, redundancy, and a more complex system is always more expensive. So instead of, well, battling against outages, I propose that you start dealing with outages and you make your system clever enough to start dealing with these outages and then recover itself. Before we dive into those details, let me first explain what we found there, because we were asked by this customer, the storage operator, to help them replace an earlier system. When we came in, the earlier system was running and they were doing manual deployments every month. So during the deployment weekend, somebody would take a USB thumb drive, walk up to a server, put the old binaries somewhere safe, hopefully, and then put in the new binaries. And of course, during this deployment, the system would be unavailable. So they would have to claim maintenance hours for this unavailability. There was no telemetry flowing from the system. So the system does talk with, for example, the compressors that make up the, that take care of the gas storage, pumping gas in or taking it out again. But if that system was offline, then the system didn't know how to deal with that. And then simply it would crash and any data being processed at that time would be lost. The system was also running on a single machine. So if there was a need to grow its capacity, maybe add a little bit more memory or disk space to it, then again it needed to be offline, powered down, modified, and then booted up again. And if there was ever a hardware failure, then, well, hopefully we would have some spare parts there. So really not a situation you want to be in. And finally, because this system assumed the availability of the remote systems, it would generally crash. When we came in, we decided to do it radically different. So this was not a company used to running stuff in the cloud, so we had some explaining and some convincing to do. And, well, these are some of the things that we mentioned to the company that, well, the cloud could bring them. The cloud is really easy to scale. So if you need more compute, if you need more data storage, anything, it's just a click of a button and a deployment away. So, yeah, it's really just, it can grow and shrink with the demand that a system needs. It also comes with excellent SLAs. So if you look at the SLAs that our Azure services provide, it is almost always 3 or 4 nines, and that's really good. The cloud is also built for speed. And what I mean with that is that, well, the cloud offers all these services like, well, storage, queuing, compute power on demand, scaling, networking. So that really allows us as software developers to focus on building features instead of having to take care of all this first and then adding the features. Cloud also brings us many failover options. So, well, in Azure, if you store a bit of data, then it's always copied at least 3 times, so it's, well, redundantly available, and you don't have to do anything for it. And if one of those copies fails, then it's up to the cloud service provider to fix it for you. You don't have to be called out of bed. They will just do it, and, well, you pay for the operations, and that's about it. The cloud is also a really secure and compliant way to run your application. So the cloud offers, of course, the ability to deploy our infrastructure as code. So we define in templates what our infrastructure should look like, and then we can deploy it automatically. And then, well, if there's no human touching this infrastructure, that means that it can be audited by simply having a look at these files. We can also make use of Azure policies. And policies will make sure that we can never deploy infrastructure in a insecure way. So we can always make sure, using these policies, that our infrastructure is compliant to the rules that we define. And finally, we can do isolated networking. So instead of everything flowing through the internet, we can make our own virtual network inside the cloud, hook up all the services that we need, and have very short communication lines. And finally, we have these premium SKUs available in the cloud. And these are really beefy virtual machines that you can run on, excellent databases with very low latency, excellent performance. So really the best of the best in hardware, with even better SLAs than the regular SKUs. There is a catch there, though, and it will come up. When we built the system, we followed a couple of architecture principles. So as a team, we decided that we wanted to build autonomous business capabilities. And that means that we divide the domain into different parts. So every functional part of the gas storage domain will be able to run on its own. And that means if one of these services that we built goes down, the other services should not be bothered by it. And the way you can do that is by introducing asynchronous communication instead of synchronous. So to put it directly, we don't do service-to-service calls, we only do pub-sub messaging. We built these autonomous business capabilities as scalable and versioned units. And that means scalable means that it can be sized to the need. That means if we have demand for more performance, more throughput, then we can scale one of these units instead of having to scale the entire system, which is, well, more cost efficient. And by running multiple versions side by side, we can make the coupling between teams lower. So if a team is using my data contracts from version 1, I'm introducing version 2, then they will have a little bit of time to start adapting version 2. So a change on my end does not necessarily mean a change on their end, giving the teams even more autonomy. We also made sure that the system was very developer-friendly. And that means, well, first and foremost, autonomous teams. So they can decide for themselves when to start releasing their stuff into production. We also do F5 in 5. So assuming that a new team member has a working laptop with some software pre-installed, it is just a matter of pulling the repo, hitting F5, and they can be productive. And the way we do that is by using a lot of containers. Especially on local host, we can make sure that all the systems that we use in Azure have counterparts that we can run as containers on local host. So you can even work offline. If you zoom in on which services the whole gas storage domain makes up, you can see that there are a few functional distinctions to be made. So the first one, and the most important one, is dispatch. And this is where customers, energy companies, go and start requesting either injection or withdrawal of gas from the storage. Each and every one of those customers has a contract that specifies how much gas they are entitled to put into that storage and at which rate they can take it out or put it in. And these are the capacities I'm talking about. If one of these customers has too much capacity or too little, they can start trading excess capacity among each other. So it's very much like the stock market here. So if I have too much space available, I can sell a little bit of that space to you, and then everyone is happy. And of course, the storage operator gets a cut from every transaction being made. And this is done in the finance domain. So the finance domain, it will monitor all the transactions being made in the dispatch in the trade domains. And then for every line, it will, well, calculate what the invoice would be sent to the customer. And finally, everyone wants to have some insights in how full this storage is, how much of their contractual capacity they are using, how much they have been using, do they need to modify their contracts? Well, all these insights, they can be made in the the reporting domain, which is also constantly monitoring all the changes in the other domains, storing it in a data warehouse so you can make nice cubes and charts. Right, so I already mentioned that the dispatch service is the most important one. And well, this is why it's featured in my demo as well. So let's zoom in a little bit on the dispatching service. So this is a single page web application front end, which the customers can use to log into. And then they can start getting some insights in how their storage capacity is doing, and start requesting injection and withdrawal. Well, a front end always needs to talk to an API, of course, and this is the dispatch API. This is a .NET Core web API. It will receive these requests coming in from the front end. Whenever the plant needs to be contacted, it will not do service-to-service calls. No, it will send messages. And then at some point, messages will come back. And if the front end needs to be notified about any changes, we can use SignalR for that. So we can do asynchronous pushes of changes to the front end. And well, I already mentioned the plant API. This is where the actual compressors are that are physically part of the gas storage and the network. This is where the magic happens. So dispatch API says how much, and the plant API will actually do the dirty business. It's important to know, plant API, it has an API. So you can ask it how it's doing, but you can never tell it to do stuff. You can only ask queries, how are you doing? What is your health state, for example? Nothing operational. So the way this works, this demo works, is front end will send a message to the dispatch API, which is REST call. This dispatch API will send a message on a queue. At some point, the plant API will pick up that message, start processing it. In reality, this can take hours, weeks, months, because you can plan ahead. In my demo, it's almost real time. Once the plant is done, it sends a message back to anyone who is interested. In this situation, it's the dispatch API. It sees, oh, my order was processed, so it notifies the front end using SignalR. Well, of course, I cannot show you the real system. That won't work, but I did create a nice demo using all kinds of fancy new features like Blazor WebAssembly, Dapr, Docker. Every cool stuff is right in here. And the cool thing is, it is open source and it's free for all to get. I do have a nice reason to use Dapr, by the way. I wouldn't necessarily say it's production ready, but for demos it's really a killer framework. And this is because it allows me to easily and simply create a solution that uses a state store and a message pops up system. So these are just components readily available, and I can configure my application in a matter of seconds to start using this storage. The cool thing is, Dapr has abstracted the actual implementation from the interfaces. So if I say I want to use a state store, on my laptop I can choose my state store to be a Mongo database running in a container. And if I'm running in Azure, I can be running on Kubernetes or container apps, for example. My state store could be an Azure storage account. And by simply changing a little bit of configuration, I can target different stores and I don't ever have to change my code. Kind of a killer feature in this case. Finally, I already mentioned we're heavily relying on containers. So, well, this is where Docker Compose comes in. And don't worry, I'll show it all. But Docker Compose, you can use it from Visual Studio to not only spin up your own written code, but you can also spin up, well, this MongoDB I was talking about. And you can spin up the Dapr sidecars and, well, and just a matter of F5 and you can do debugging. So it's kind of a powerful mechanism there. So let's switch to, I'll show you the working demo first. So don't worry, it's very simple. This is my current view of the gas storage. I'm in the dispatching domain. I have logged in as a customer. And now I can say, well, I want to inject 12, for example. And then you see a blue pop-up there, and that means that a message was sent and a message was received back, and well, all that stuff happened in the background. And the way this works is, well, by Docker Compose. So if you look at this Docker Compose file, and well, it won't take forever, so if you're not familiar with Docker Compose, just close your ears for a minute, but if you are, this may be interesting. So this is my dispatch API. This is a Dapr sidecar attached to it. So yeah, I'm not going to go into details about that. The plant API Dapr. And this is the way you can run this in production. But I'm not running in production. I'm running on my laptop. So I want to do an addition of some helper containers. So like I mentioned, I'm adding MongoDB as my state store. I'm adding Mongo Express as a way to look inside this Mongo database. I'm adding Redis for PubSub messaging. And you guessed it, Redis Insights to have a look at what my PubSub messaging system is doing. So I not only have a working queuing system, but I can also see inside that queuing system what's happening. Well, you can see that happening here. So this is the Redis Insights container. I've already sent a few messages by requesting storage. So if I hit this button a couple of times, it will start doing stuff, and that stuff will immediately show up here. So if there's an issue, I can probably locate it here if the issue is in my messaging system. I can even go into these messaging streams and see the exact data that was sent over the wire. So this is a request flowing in, and this is a response after processing. And for example, you can see, well, this one has succeeded. And the same thing goes for the telemetry about which information is flowing between the services. So I can run a query here. I need to be faster, so let me quickly hit this button a couple more times. And now quickly go here. Yes. Without touching well, any telemetry at all, I just add this container to my composition. It has a magic endpoint, and Dapr will know where to send its data, and telemetry starts showing up here. I didn't write a single line of code for all this telemetry to appear here, but you can see stuff is happening apparently with the plant API and the dispatch API. And I can even make it more graphical by showing you this. I can zoom in somehow, but the left one is the dispatch API, this is the plant API. And you can see messages flowing between that. And the amount of circles that you see are indicative of the amount of traffic relatively. So, kind of cool. Zero code. And finally, if I want to see what's happening in my state store, I can have a look at Mongo Express, but this will come up in my second demo. Right. Well, how do we deploy this into production? Well, of course, we use automation for that. And we kept it as simple as possible. So whenever a developer changes code, it is written on the laptop, of course, but at some point you will push it to a central repository, in this case Azure DevOps. This will trigger a continuous delivery pipeline. So first we will compile the code, we will run all kinds of unit and integration tests against it, and if that all works out, we will generate a container image and tag it with a new version. And then we will push that container image to an Azure Container Registry. We want it to be a private registry, not just Docker Hub, which anyone can use. Now this is intellectual property here, so it's a private container registry. Once this image is available, we can talk to Kubernetes, which is our production container cluster, and we can say, hey, there's a new version available. Please go ahead and upgrade it for me. Kubernetes will then, well, it will make sure that the new state is applied, so the new tag version is the one running in test at that point. We can do manual testing, smoke testing, integration, coded UI tests, for example. And if we're happy, we take that same exact container image version and deploy that to production. Well, there needs to be a small difference in configuration, of course, because the test environment uses a test database and a test messaging queue, for example. We need to configure it to be listening to the production systems. Now, the only thing that changes between these deployments is the configuration files. So, container image is immutable and it flows through different environments. It can even run on my laptop. The trick is providing the proper configuration for the proper environment. Well, let's have a look at the Azure Architecture now. It is quite complicated, and don't worry, I will show you the holistic overview. So on the left-hand side, in the yellowish thing, we can see global services like Traffic Manager, Azure Active Directory, and all that sort of stuff. Then in the red, we have these two firewalls. The firewall on the left is an application gateway, web application firewall, and it will protect traffic flowing into the system. And the one on the right, it will protect traffic flowing out of the system. So left ingress and right egress. And both need to be monitored because, well, like I mentioned, there's a lot of zeros flowing through this system. Then all the compute runs in AKS, Azure Kubernetes Services, and we made sure that the system node pool, the one on the left, is separated from the workload node pools. And we have two node pools for the workloads. And that is because we want to run multiple versions side by side. And they cannot interfere with each other. So if one goes all the way haywire using CPU or memory, it won't affect the other version. And by simply switching using a DNS trick, we can say this is now the production version. And by this means, we can separate our releases. So we can put binaries on those nodes. We can separate the release of those nodes to the customers from the deployments of the nodes. So by simply saying green is now production or blue is now production, we can switch between versions, do fallbacks in a matter of seconds. Well, all this compute, of course, it generates a lot of data, and the data needs to be stored somewhere. Well, we have storage for binaries, we have storage for container images, for secrets, of course, structured data as in SQL Server, and all the telemetry is kept in Log Analytics. Well, the way we deploy all this infrastructure, I already mentioned, this is done automatically. And you will see this is very similar to the way we deploy our binaries, our software to production. So, same thing happens. We have this repository, we have files defining the infrastructure as code. And whenever a change is made, we can run the tests that make sure that the PowerShell scripts that we have are still valid. And then we can deploy these templates to a test environment automatically, no hands-on. And then once this is done, we know that the scripts and the changes are valid, and then we can go ahead and deploy the same changes to the production environment. Really nice. There's a catch here as well. So at some point, fortunately, before we were running in production, that was a close one, we had a really nasty surprise in our Azure bill. So what happened during the weekend, of course, there was this crash loop in one of our pods. And the pod was running on many virtual machines, so it was crashing on many virtual machines and starting over, crashing, starting over. And all this useless telemetry that was gathered by the logging agent and put into Log Analytics. And Log Analytics is one of the most expensive Azure resources if you put stuff in it. So don't put stuff in it, it's free, but as soon as you start using it, it is hugely expensive. And well, that was what happened to us. So we had a really nasty surprise in the Azure bill. It did, of course, trigger us to start thinking about cost optimization. So we had all this nice stuff in place. We were monitoring infrastructure health. We were monitoring software health. We forgot to monitor infrastructure cost. So what we did, we added spend to the dashboard. So every developer going to the portal would immediately see the current spend. And if there is a spike there, well, it will show up. That is part one. We've put hard caps on the non-production environments. So if it ever happened again, simply it would stop working, which is really nice, save money. And of course, you cannot do this in production because this is a system that needs to be up and running. So we want to be notified about costs going out of control. We don't want anything to stop working. So this is why we can have cost alerts, these so-called budgets within Azure. If we get to 80% of the budget, we will get an email. Well, somebody needs to monitor that email and do stuff with it. And this is why we also started running on-call duty at that time. We weren't in production yet, but we talked about it. It made sense. Start running on-duty calls on the system before it was even running in production. And this allowed us to get used to doing this. It was my first time running support duty. We needed to get familiarized with the PagerDuty tool, which is the incident reporting system. We could also use this time to start documenting the proper way to deal with these outages. Because, well, a lot of these outages, they happen at night somehow, and you get called out of bed. You are not as sharp as you are during the day. You want to get back to bed as soon as possible. So it really helps if you had this run book available, specifying do this, do this, do that. Make sure that this is in place and then go back to bed. So this really helped us and yeah, okay, it's good. We also had another look at the services that make up the gas storage domain. So we had a good look, we talked to the customer and we said, well, what will happen if one of these services goes down for a longer period of time? And it turned out that it was okay for all of these systems to be offline for a day, for a couple of days even, except for the dispatch domain. So as long as customers can request either injection and withdrawal, and it's actually processed, the customer was happy. So all these other systems, they were running on, well, high-level SKUs. It wasn't even needed. So we could optimize for cost there as well. So we refactored the infrastructure, optimizing for cost. So the mission critical parts, they kept running on these really beefy premium SKUs, but the other stuff, that could run on standard SKUs because it doesn't matter if it's down. And of course, every dev and test environment can always run on sub-premium hardware. We also introduced dynamic scaling. So we had a good feeling about the hours that the system would be used most. So we could scale for the peaks and then scale down for the throughs. We also added conditions to resources. So this Azure Firewall, I'm not sure if you've ever used it, but that is quite an expensive resource. And an application gateway with application firewall, also very expensive. You don't need that in your test environment, right? So who's going to hack your test environment and what will they get? Well, in our case, there's no production data there, so good luck. So we added conditions to resources, making sure that we only had expensive resources in the production environment. And well, this is the downsized architecture. As you can see, fewer icons. So fewer icons means lower Azure bill. Lower Azure bill is always nice, but it's also nice for the developers, lower complexity. Fewer icons means lower systems to interact with, right? There was a downside, however. So now our test environment is no longer identical to our production environment. So how do we know that if we make code changes that affect the production environment, how do we know that they won't break? This is something we solved later. But first, oh no, there was another outage in Azure. And this time we were running in production and I was in fact called out of bed for this one. So between dispatching, finance, trade, reporting, we always use pub/sub messaging. We heavily rely on messaging. So whenever state changes inside dispatching, a customer has requested something and it has been processed, we notify the rest of the systems by messaging, pops up messaging. You just send a message, every other system will get it. It's important to realize that dispatching needs to be able to send this message, but the other systems, they don't need to be able to receive it. So this is not part of the mission critical path, not part of the time critical path. So, you guessed it, Azure Service Bus was down, messages could not be sent, and we were called out of bed. So we needed to deal with this. And the way how, it will come up. So we decided we don't want this anymore. So let's refactor the infrastructure a little bit more. We added multiple regions. So instead of running only in West Europe on redundant hardware, we added an entire new region in North Europe. And North Europe would mostly act as a hot standby. So it would be there, binaries would be running, but no DNS tricks were done to have traffic flow to that system. So effectively, it would do nothing. It would be just standing there, ready for action, but not actually doing that. But for queuing, we thought, well, a message can easily be posted to the secondary queue and then be received there. The only thing that we need to do is have a little bit of magic deciding which message queue we are using. And on the other hand, we need to start listening to 2 messaging queues. Well, then we pay for all these resources in 2 regions and actually use them. So that's a nice benefit. So this is one way to solve the queue unavailability issue. Of course, we have this environment in the secondary Azure region now, and it's running, but how do you know it will work when there is a disaster? So we decided we wanted to do a failover at least once per day. So every day that we were in the office, we would start by doing a failover. And then it would work or not, but we would find out really fast. And then if there was ever a need to do a failover because of an outage in Azure, we would just have complete faith in this process. So now it will work. You could just get out of bed, hit the failover button, go back to bed. This is how much faith we had in the system. Of course, you want to check if the problem has been resolved, but you know where I'm going. It's no use to have a secondary environment if you do not absolutely know for sure that it's actually working. And that means, well, you need to eliminate single point of failures. You need to have redundancy for everything, every part of your system. You need to duplicate infrastructure, so you have 2 elements of compute running, you have 2 data stores running, and okay, well, if you have 2 data stores running, you need to deal with some issues, of course. So, compute in the green part, that's easy. It's stateless, it will just scale all over the planet, and well, it doesn't keep any data, so you never need to look for your data. It will just work. But the red part, the data stores, they need special care. So, for databases, we use Azure SQL, which comes out of the box with a really nice feature. It's called geo-replication. It's just a feature you pay for, and it will allow you to have 2 databases running in 2 separate Azure regions. You say this is now the one to talk to, the primary one, and Azure will make sure that all traffic goes there, the data is stored there, and every bit of data stored there will be copied there. You can do failover, you can do failback, you can switch multiple times per day. The switch is always done while waiting for pending transactions, so you never lose any data unless one actually explodes. So, really solid process. Definitely something to recommend. Well, if you have a look at blob storage is a totally different beast. So blob storage does come with a built-in failover option, but the state of the system after failover is a single region copy of your data. You will need to make sure that it becomes a geo-redundant system again, so copies the data back to the original region. And there's no warning at what point in time this is done. So that's not something that we felt comfortable using. So we decided, well, we don't generate a lot of blob data every day. When we do a failover, it's just momentarily. So why don't we just bring the data that was generated in the secondary region back to the primary region when we fill back? And that works really well for us. So we just have two databases, and if one has data, we copy it over to the primary, which is our favorite location. And I already explained about PubSub messaging. We just have two queues running active, and if one queue fails, we send it to the other one. And that works really well. Only sometimes you get this message and you get it twice, because the sending party, it said, well, no, I was unable to send the message. But the message queue did in fact crash after receiving the message. It happens. And then you get two identical messages flowing into your system at one point. And then, well, you need to deduplicate it, of course. Fortunately, Azure Service Bus has built-in capabilities for message deduplication. It's not the holy grail, but at least it's something. So what we did is we brought back the processing of messages to a single instance. And then, well, we keep a list of messages that we already processed. And as long as that list is persisted somewhere safe, you can always see, okay, I already processed this message, so I can discard this one. And finally, we made sure that if a message was processed twice, it would not have side effects. So processing the same message twice, it is even okay. Right, well, let's see how we deployed this new redundant infrastructure. It is very similar to the infrastructure deployment we saw before, but what we now do before we deploy our production environment, we will first deploy our secondary region. Then we can test it, and if everything is well, then we can make the secondary region our primary, our main region. So the secondary becomes the active one. That gives us the opportunity to take down the primary region and replace that. And if everything is happy, tests work out, everything is good, we can switch back to production and do the fillback. The cool thing is, now we have a place to test our infrastructure changes. So if we have production level infrastructure changes, we can apply them to the secondary environment and find out if these changes are in fact okay. So problem solved. Right, well, we did not only look at our services, which parts of the services are not mission critical, we also looked at our Azure infrastructure. So the red parts in the Azure infrastructure are mission critical, and it's absolutely vital that these are online at all times. So if we don't have ingress, well, we cannot receive any dispatching requests, of course. If we don't have compute running, well, nothing is listening to the ingress. And if we don't have our database, then we cannot fetch any contracts, so we cannot validate what is coming in. So these are absolutely necessary for the system to be alive. But all the other stuff, and mostly the data-related stuff, we had a look at and thought, well, what can we do to reduce the coupling to these data stores? So for Azure Storage, for the container registry, for Key Vault, we looked at each one of them and then decided, well, what can we do to lower the direct dependency to these remote systems? And that brings us at the next level of this presentation, and that is dealing with outages by adding resilience. And this is more software architecture related. So first, we start cutting dependencies. Like I mentioned, start cutting the dependency to storage, Key Vault, all these services that, well, that can be worked around in case of failure. We added some nice design patterns like the Retry pattern and the circuit breaker. And we started caching a lot of data locally. So fetch it first and then start processing based on that information instead of the actual remote systems. And the last, one of my favorite design patterns is the outbox pattern. And it will come up in a nice demo. But first, the retry pattern. This is absolutely vital to have in your cloud-native environment. So the software systems that you talk to, they are often offline for just a millisecond or two. So it really makes a lot of sense to add some retry logic in your system whenever you are calling remote systems. So what you do is you just simply wait a little bit and then try the operation again. And you will see that usually it succeeds. Of course, there is a chance that the caller thinks that it failed, but the receiver actually got your message. So same as messaging here, you need to make sure that your systems processing those messages are idempotent and they are able to detect duplicate messages coming in. You need to be very sensible about this. So if you have a validation error coming back from your API, it does not make sense to retry it. You can retry it as long as you want. The validation error will never go away. But if you get a server timeout or a deadlock from your database, then it all of a sudden does make a lot of sense. So, and if one of these retry operations saves you from being called out of bed, it's already worth the effort. You do, of course, need to be aware of the consequences. So any operation that you perform on this remote system, it will statistically take longer to complete. But in exchange for that, you get a higher chance of success. And if this system out there does have an issue that takes a bit more time, it could result in a lot of systems trying to do retries calling on that system. And if it does become available, it may have a surge of pending requests process, bringing it down immediately again. And there is something to do in that area as well. But first, let me show you a nice demo of the front end, which is my dispatching front end. It wants to do a REST API call on the back end. And that API call, it will be, well, kind of crappy. And that is because I have this. Okay, in my front end, I want to fetch the amount of gas currently in my personal store. So I've logged in as a customer. I want to see how much gas I have in this store. This operation is called. So this is the operation running on the dispatch API. It will do an HTTP GET and get the gas in the store for a certain customer. And as you can see, I've added a bug there. So about 70% of the calls to this API will fail, and they will result in a 503 service unavailable. And if you remember correctly, this is an operation that makes sense to retry because the server may be available the next time you try it. All right. Well, then you can probably imagine when I want to call this API, I have a little bit of code for that in my front end. And because I use Blazor, my front end is just C#, nice and readable. And, well, when I want to get my gas in store, you would probably expect there to be a while loop here and do retries and examine results. But I don't want that because I'm making many HTTP calls all day long. And I don't want to have that retry behavior around every call I make using the HTTP client to the API. Fortunately, we can tweak this class here, HTTP client. We can tweak it using an open source library to incorporate built-in retry behavior. And for this, I've used Poly. Poly is a library you can just get off the internet. It's open source, it's very popular, and well, it worked really well. So the way you do this regularly in plain old ASP.NET Core is add HTTP client. You register it as a service so it can be used for dependency injection. But now I'm adding some voodoo there using this policy builder. And you can see I'm adding a fallback policy and a retry policy. So the retry behavior is, well, try it again if there is an error that makes sense to retry. And the fallback policy is something you do whenever, well, you try it again, it didn't work, now what? Well, then you get the fallback policy. If you have a quick look at that, you can see, well, I've configured policy for transient HTTP errors. I will do a wait and retry. And because this is a demo, I will only do one retry, and that works for me. In real life, you would probably do a couple more retries. And then, as a fallback policy, I will simply invoke this value factory delegate, which returns -1 as a static value. Well, let's see it in action. I will open my developer tools here and make sure that it's clean. When I call that API, well, we're in luck. So it failed twice. So that's simple statistics happening here. I configured it to do one retry. That means 2 calls in total. One the try, one the retry. And then, well, it failed. So it went to the fallback policy and said, well, I'm returning -1 for this. And this means that the customer, it does see bogus data, but it can continue to work. So even though there is an issue somewhere in my system, a buggy service, the functionality is mostly still there. We call this degraded functionality. You can still do requests because that API is not buggy, but fetching the state is a little bit buggy. So I can try it again. And then, well, of course, that's almost not statistics anymore. But now you can see 240, which is the actual value. Poly to the rescue. Right. I did this, yeah. Okay, well, remember me saying that there could be a surge if the backend system all of a sudden comes online after, well, a lot of people have been waiting for it to come online by using the retry pattern. So how can you avoid this? So you can detect this outage downstream and then say, well, I know who you are. I know you want to call the backend, but the backend isn't available, so don't even bother. And this is what the circuit breaker pattern does. So it's a switch somewhere in your HTTP client, and it will say, don't even go there and go to the fallback policy immediately. So this prevents waiting. So instead of having to wait for all those retries to finish, to find out, for the customer to find out, yeah, there is in fact an issue somewhere in the system, you can immediately provide feedback. So if the circuit breaker says, don't even bother, you can catch that exception and say, well, there appears to be a problem, try again tomorrow, for example. So this prevents a lot of people building up and queuing in front of the remote system. Of course, if you use Poly, then you will need to have some kind of logic dealing with this circuit breaker open exception. And this is something that you need to do and talk to the business about. So what happens if this API is not available? And then to recover, this is not like the actual circuit breaker in your house. You flip it back on and current starts flowing again. In software, re-enabling this circuit breaker is generally an analog process. So first you let 10% through, then you let 50% through, and then you go all the way to the 100%, for example. And by this means, you have an additional safety measure to prevent these surges from happening downstream. Then there is, of course, distributed caching. So instead of fetching stuff freshly from the database, why not just take as much of that data as you can, slowly changing data, copy it local and use it as a fallback mechanism. You need, however, to make sure that this data stays fresh. So you need to have a mechanism in place, for example, listening to messages or whatever you choose. You need to make sure that your data stays crispy fresh, so you're not working on an old version of the truth. You can do that 2 ways, asynchronously by sending messages whenever the data changes, or synchronously whenever you want to query something, you first try to query it in the remote system and then update your cache on the way back. That is called read-through caching. Well, it makes a lot of sense if you are in a orchestrator environment like Kubernetes to store this data on every node in the cluster, making it highly available. So if one of these nodes gets killed because of scaling or it dies because of an error, you always have the remaining healthy nodes to use as a copy of your data. Then my favorite pattern, the outbox pattern. And this is, well, have you ever wanted to send a message to a service bus, for example, but only if a local transaction succeeded? So you want to change the gas in store for a customer and notify the world about it, But if the transaction on the database fails, you don't want to send that message. And if the message fails, you don't want to do the transaction. Well, that is a problem that, well, in the old days could be solved with a distributed transaction coordinator. Fortunately, we don't use that anymore. But there's a simple pattern you can use to avoid this problem. So you buffer your data in a table in your database. And you do that in the same transaction that modifies your other data. So the change to the gas in store, you will combine that with a message you put in a table instead of on the service bus. And if it's in the table, in the same transaction, it is either completing or rolling back, but both changes are done at the same time because it's in the same transaction. And then at that point, you can start processing in the background. You process this outbox and start trying to send this message out. And if it doesn't work immediately, that's okay, because you're now in the background thread. And well, at some point you know that your queuing system will come back online. So at one point it will work. So you will have sort of guaranteed delivery. Well, the benefit here is that you don't need a distributed transaction. You can make your changes on a database instead of on a remote system and a database. And the added benefit here is that if you ever have a lot of stuff to send out, putting it in a queue first, in the queue in the database first, can flatten the peak. Well, 3 minutes, that should be fine. I can do a nice demo here. Right, so the system is up and running. I have already mentioned that I'm using Redis pub sub messaging as my queuing system. Redis is running as a container here. I will now stop that, kill my pub sub messaging. And now I will go back to my user interface, clear this, start sending requests. Well, what you should see is that the gas in store is not changing, but my service, so my API is returning 202. So it received my message. It was able to change my data inside the dispatch API, but it could not talk to the plant because the messaging is down. But that's okay. My messaging will now come back to life. Keep an eye on this here. And then if the demo gods are favoring me, then at some point my messaging system will come back online and the pending messages will be processed. Minimal effort. It's like a few lines of code to build this using Dapr. I genuinely invite you to have a look at the project. Just a few lines of code and a very resilient system. Right. Okay. Yeah, almost there, wrapping up. I won't go over all of these, but if you want to make a picture of this, be quick. And if not, I will have a couple of useful links for you to visit. So the top one is the source code of the demo. Below that is a link to Polly. If you want to reach out and get in touch with me with further questions, please do so using LinkedIn. And if you want to know more about Xspirit, have a look at the final link. And finally, if you want to earn a lot of swag, take this Microsoft challenge, and then, well, you need a UK address, if I'm not mistaken. But, well, there's a good likelihood that you have one of those. That's it. That's my talk. If you have questions, please come up and see me. And thank you very much for being here.